John.
All right, thank you, Lars. Thank you all for coming. Honored to be talking to you. So I think my charge is to give you an idea what our program on the quantum physics of information is about. I'm not sure how well I'll fulfill that charge. I will give you my perspective on our field and the things we're trying to do. I imagine other program participants would tell you a different version of the truth. I got involved in quantum information science in the mid-90s, soon after Peter Shor discovered the efficient algorithm to be run on a quantum computer for factoring large numbers. And I was really deeply impressed at the time by the idea that the difference between hard and easy problems, the ones we can solve someday, the ones that are out of reach, that the answer to that question is different in a classical world than a quantum world. And in the 20 years or so since then, I and a lot of other people have focused a lot of effort on answering questions about quantum computers, such as what will we be able to do with them? Can we really control them? Can they be built? What should the hardware be like? And so on. And there's been a lot of progress on those questions. And now something kind of interesting is happening, a bit sooner than I expected, that there is a sharp ramping up of interest and investment in industry in quantum technology. Big players like Microsoft, Google, and IBM, and also quite a few startup companies that are leaping into the fray, fueled by a lot of venture capital investment. And we always knew that the task of building large-scale quantum computers was something to be carried out by industry, but these recent developments call upon us to ponder what the mission should be for those of us who are doing quantum information research in an academic setting should be, as a lot of activity is ramping up in industry. And there are several ways of answering that question. I think one way is that what industry is doing now is building on the fundamental research that's been done over the last 20 years. And so we should be attempting now to lay foundations for further initiatives that industry will undertake some decades in the future. But more than that, really, most of us don't see quantum information as a field of technology. We think it's an important field of basic research, that we are really in the early stages of exploring a new frontier of the physical sciences. I like to call it the Entanglement Frontier. It's really a way to explore nature that hasn't been available to us before. We are in the process of developing and perfecting the capability of preparing and controlling precisely and studying a very complex many-particle quantum systems, highly entangled systems, which surpass what we can simulate with our digital computers and in many cases are not well suited for analysis with our existing theoretical tools. So we can anticipate that as we probe more deeply into this entanglement frontier, we'll discover new emergent phenomena that we hadn't anticipated, just as when we build a new particle accelerator or a more powerful telescope, then we're able to probe more deeply into nature. And our conviction that this is going to be a rich frontier to explore is based to a large degree on two central ideas that I want to talk about. The one is quantum complexity, and the other is quantum error correction. So by quantum complexity, I mean that for a relatively small quantum system, if we wanted to describe using classical language a quantum state, that there's no succinct way of doing so. So, for example, if I have a system of n qubits and two-level systems, the dimension of its Hilbert space is exponential in n. And so if I wanted to write down a state vector, I would have to write down a number of complex numbers, which is exponential in n. And that already becomes beyond what's feasible for n of about 50, where I need petabytes of storage to store the quantum state, and then updating the state as it undergoes a quantum computation or evolution according to some Hamiltonian of interest is beyond what we can do with supercomputers today. And that statement is fine as far as it goes, but it's a bit misleading in two respects. One is that whenever I do an experiment, I'm going to measure the state in order to find an outcome. And in a single shot measurement of n qubits, I can't collect more than n bits of information. So there's a dark veil separating us, the observers, from this kind of extravagant complexity of the quantum state, and exactly how much of the extravagance we have access to is a good question. And it's also misleading in another way, which is that a typical quantum state may be very difficult to describe classically, but we're not normally interested in typical quantum states. In fact, the quantum states that we're ever going to encounter in nature, or that we're ever going to be able to build as future quantum engineers, is just a tiny part of this exponentially large space. As a cartoon, if this is the Hilbert space, what we'll ever be able to get to is just some tiny, tiny island in this Hilbert space. But here I'm drawing the geometry not in terms of the usual Hilbert space metric, but rather as in terms of a kind of metric, where distances correspond to how hard it is, how complex a computation we need to carry out to get from one state to another. So another way of saying it is that if I start out in a quantum state that's easy to describe, like a product state of n qubits, each of which is pointing in some specified direction, say, and then I let the system evolve for some reasonable amount of time under the control of some reasonable Hamiltonian, the states that we'll be able to reach are just a tiny part of this huge Hilbert space. By a reasonable Hamiltonian, I mean one which can be written as a sum of local terms. That is, the Hamiltonian is a sum of terms, each of which acts on some constant number of the qubits, independent of the system size. So let's say a k-qubit term with respect to some decomposition of the Hilbert space into qubits. And by a reasonable amount of time, I mean a time that doesn't grow faster than some power of the system size. So you can ask, well, how confident are we really that we can go places in Hilbert space that are hard to describe classically? And part of the evidence for that comes from the existence of quantum algorithms that have been constructed, like Shor's factoring algorithm, which seem, when we build quantum computers, to be able to solve problems which we think are hard classically. We don't really know that the factoring problem is hard arguing from first principles. Our confidence that it's hard is based to a large degree on the fact that very smart people have tried to find more efficient classical factoring algorithms for a long time, and the best algorithms still have a complexity that rises super polynomially with the number of bits in the integer to be factored. And at any rate, we're not going to be factoring very large numbers with quantum computers probably for quite a while. Because to solve a factoring problem which surpasses what we can solve classically, that means factoring something that's probably thousands of bits long, and that would require, in a quantum computer, a number of qubits, which is at least a few thousand, and a number of elementary operations, which is in the billions. And that's assuming we have a noiseless quantum computer, which we don't have, and there will be considerable overhead cost in controlling the errors in the quantum computer, so that in practice we'll probably need millions of physical qubits in a quantum computer that can solve a factoring problem that surpasses the best that we can do classically. But what about the near term? Well, where are we? So now, if we look at what some of the industrial enterprises are doing, IBM has a 16-qubit quantum computer. It's in the cloud. You can go visit the IBM quantum experience and run a quantum algorithm on it. people really do. They had a previous generation of their cloud interface quantum computer which had just 5 qubits, and it was used by thousands of people, including a lot of undergraduate students doing quantum computing labs, and they intend to continue scaling that up further. Your neighbors, Google.
What does
Question.
it mean it's in the cloud? Where is it?
Google, IBM Quantum Experience, and follow the link, and you will receive instructions about how to get access to it and run a quantum algorithm on it. Oh, you mean where is it located? It's at IBM in Yorktown Heights.
And what are the qubits?
Oh, good question. So the technology being pursued by both IBM and Google is qubits encoded in superconducting circuits. Now that's just one of the technologies which has been continuing to advance for some time. The two most advanced currently are ion trap quantum computing and quantum computing with superconducting circuits. But there are a number of others which are making important progress, one of which I'll mention later. Google is kind of tuning up a 22-qubit quantum computer, and they have plans in the not-too-distant future, maybe next year, to have 49 qubits in a general-purpose quantum computer. And that's sort of getting us into the territory where brute force classical simulation of what it does is infeasible. So these are general-purpose gate-based quantum computers that can, in principle, run any quantum algorithm of the appropriate size. But advances are also being made in analog quantum simulators. Quantum simulation of many body physics using, for example, ultra-cold atoms and optical lattices has been an interesting enterprise for about 15 years now. But what's happening now is the quantum simulators are becoming more sophisticated, more programmable, and capable of studying a range of problems with longer-range interactions. So, for example, at the University of Maryland, they have a trapped ion quantum simulator with 53 ions. And at Harvard, a 51-qubit quantum simulator, which is based on neutral atoms assembled using optical tweezers. And in both cases, although these aren't general-purpose quantum computers, they've used these simulators to study dynamical phase transitions in Ising-like systems that have long-range interactions, which go well beyond what we can currently simulate with classical computers. But what can we say about how confident we are that with these relatively near-term quantum computers, we'll have general-purpose quantum computers with 50 to 100 qubits in the next couple of years, so naturally there's a lot of interest in what we can do with them. Nobody really knows. But the complexity theorists have been kind of helpful in, building an argument which is reasonably persuasive that systems of this intermediate scale, let's say 50 to 100 qubits, are capable of producing states relatively easily, something that could be done with the technology we'll have in the next couple of years, which are in a sense beyond the classical. That is, the argument points to the conclusion that if you measure all the qubits, the probability distribution of outcomes is not one that can be sampled from by any efficient classical algorithm. So in that sense, the quantum device would be doing something that we think goes beyond classical. And what would that be good for? Well, it might be good for doing new kinds of variational algorithms. We could, for example, try to find the ground state of a spin glass, or approximate the ground state of a spin glass, or from a computer science point of view, try to answer the question how many clauses in a Boolean formula can be satisfied. Well, that's a very hard problem in worst-case instances, and we don't think even quantum computers can solve it in hard cases. But it may be that the quantum computer will have advantages for finding approximate solutions. That is, say, finding the energy up to some multiplicative factor might be done faster with the quantum algorithm than a classical one. And in that mode, we speak of quantum approximate optimization algorithms, which were proposed a couple of years ago by another lapsed particle physicist, Eddie Farhi, and his collaborators, where one prepares a state, measures its energy, then tweaks the state and tries again in order to get an estimate of the energy. And we can apply the same kind of procedure to trying to solve quantum problems, like finding the minimum energy state of some Hamiltonian that might be of interest to the quantum chemist, like describing a relatively small molecule. And in that guise, we speak of variational quantum eigensolvers, where it may be that in the relatively near term, the quantum computer will be able to achieve speedups in estimating ground state energies compared to the state of the art in computational chemistry on classical devices. But I think probably the most promising thing to study in the near term is just quantum dynamics, because that's something classical computers are especially bad at in strongly coupled systems that are highly entangled, where potentially a quantum device could really knock the socks off a classical device. And in particular, it'll be interesting to study the behavior of quantum chaotic systems that are strongly coupled outside the regime where we can do classical simulations. If you look at the history of classical chaos, it really took off when people started to use classical computers to simulate dynamical systems, and we might anticipate that something similar will happen in the study of quantum chaos as quantum computers scale up. Now, I keep emphasizing that we're not sure whether these things will work. People will try them in the not too distant future. And part of the reason we're not sure they'll work is because quantum computers are noisy. Even after a lot of work, going back over a decade, in all the different technologies, which involved better materials, better fabrication, better control methods, in the most advanced technologies, superconducting circuits and ion traps, doing a 2-qubit quantum gate can be achieved with, roughly speaking, a probability of error per gate, which is a little bit below 1%. So that means that in these near-term applications, we're going to want to find a balance between two things that we desire. On the one hand, we would like the problem to be sufficiently complex that we think it's hard classically, or at least beyond current classical technology. And at the same time, we don't want it to be too big an algorithm with thousands of gates. Probably we'll just get junk and the signal will be completely lost. So we're just going to have to try it and see how well it works in these intermediate scale applications. Now, in the longer term, if we want to scale up quantum computing, this is where quantum error correction will have to come in. We'll have to get errors per gate which are far smaller if we want to run long algorithms with a reasonable probability of success. So the idea of error correction is that we have some set of errors that we want to correct, which are operators acting on our Hilbert space, the types of errors that we think are reasonably likely to occur. And we have, let's say, a qubit that we encode in a complex system of many physical qubits, which has orthonormal basis states, which I'll call 0 and 1. And then when these errors occur, we would like these states, which are ideally orthogonal, to remain perfectly distinguishable. So when arbitrary errors of the type we want to be able to correct act on the states, they remain orthogonal. So the basis states may get deformed in some complicated way, but as long as they remain distinguishable, then in principle we can decode the information. Except we're talking about errors in a quantum system, so we need to be able to protect superpositions of the basis states. So at the least, we would like to consider states in the dual basis, which are mutually orthogonal and demand that they remain distinguishable after errors act. And so if we put these two conditions together, both of which should be required if we can recover from the errors, we draw the conclusion that if I consider any operator of the form EA adjoint EB, where EA and EB are the types of errors that we're worried about, it should have the same matrix element between the two basis states, 0 and 1. So you can think about it this way. If I imagine, just to be concrete, that I lay out the qubits, the physical qubits that encode the information in some two-dimensional array, and then somebody punches a hole through the system and removes some of those physical qubits, I would like still to be able to perfectly distinguish these orthogonal states. And so what that's saying is that any operator which is localized in that region that's been damaged should not carry any information about what the logical state is. By measuring any operator in this erased part of our physical system, I shouldn't be able to tell the difference between the 0 and the 1. Okay? So the idea of quantum error correction, more broadly speaking, is we'd like to encode information globally in some way in a system with many physical subsystems, but such that when we look at the parts of the system, one by one, there isn't any information in any one of these localized parts that tells us about the globally encoded information. Okay? And then when the environment interacts with the system, the information needn't necessarily be damaged. And that concept of globally encoded information, which is locally inaccessible, is a familiar one to the condensed matter physicists. It's what we call topological order, which can occur in suitable, highly correlated electron systems, like systems that exhibit the fractional quantum Hall effect. And in fact, the best idea we currently have about how in the near term to protect quantum information in a quantum computer is to follow this paradigm of topological order so that we envision, with whatever our preferred technology is, say superconducting qubits, to lay out the qubits in some planar array where the physical system is realizing a kind of simulated topological order. When there's topological order, we also have charge fractionalization and particles with non-trivial Aharonov-Bohm type interactions, the simplest version of which is just a Z2 gauge theory, where we can have excitations of the electric and magnetic type such that when one is carried around the other, there's a Aharonov-Bohm phase of -1, which can occur even at long range. And the reason this charge fractionalization is associated with the ability to encode information, well, normally in case of condensed matter physics, we think there's some Hamiltonian. It has a degenerate ground state. We can encode information in the ground space. There's some mass gap so that, at least at low temperature, we have a high probability of staying in the ground space. But it's the fact that it's degenerate that allows me to encode non-trivial quantum information. And if I imagine that I have a system where the electric type excitation can disappear at one of the boundaries or appear there, we can imagine a process in which the electric excitation appears at the bottom and propagates across and then disappears at the top, and the magnetic excitation appears at the left edge and propagates across and disappears at the right edge. You can think of those as two operations that take the ground state to the ground state. These excitations are the excitations which can be locally observed when we get excited out of the ground space. And if the excitations disappear again, we're back in the ground space. But these are two operations acting on the ground space which don't commute with one another. Because if I change the order in which they're applied, I get this -1 arising from the Aharonov-Bohm phase. And so that means that the existence of the charge fractionalization allows me to infer that the ground space must provide a representation of some non-abelian algebra, and that means it can't be one-dimensional. So we can store quantum information there. And so what we imagine doing is making our quantum computer behaves like such a system, and then we regularly measure the system to see if these defects, quasi-particles carrying the Z2 electric and magnetic charges, appear. Well, when they're created, there's a locally conserved charge, so they tend to be created in pairs, which are strongly correlated. And then once they're created, they can start diffusing around due to whatever kind of noise is affecting the quantum computer. So we just continually measure to see where those quasi-particles are. The measurements are noisy because everything's noisy, but because they're repeated many times, we get pretty good information about what the quasi-particles are doing. And the logical information can be damaged if a pair gets created and one member of the pair goes to one edge and the other member of the pair goes to the opposite edge. But it's okay if whenever that happens, we know that it happens, and that means the error is correctable. And that's how people are proposing to achieve a very long-lived logical qubit in the relatively near future with more or less existing quantum technology. And we'll see in the next few years how well it works. The expectation is that we should be able to produce an encoded qubit with a much, much longer coherence time than the natural coherence time of the physical qubit. Steve?
But that means you need to have a lot of physical qubits.
Yes.
For your...
That's right. So that's why, depending on how high the error rate is, we will need a lot of redundancy. We always need some redundancy in order to protect against errors, and how much we need depends on how noisy the system is.
But I guess to have topological order, it at least has to be bigger than some correlation length or something.
Yeah, but the correlation length could be comparable to the lattice spacing. Yeah. Of course, we want to do more than just store qubits. We want to be able to process them. And we understand more or less how to do that in a device that realizes this kind of encoding. So, the more ambitious goal is what we call fault-tolerant quantum computing, which basically means there's some family of quantum computations that we'd like to perform, and that by performing them at the encoded level rather than just with the physical qubits, we can make the probability of error for the whole algorithm smaller than if we didn't encode. That hasn't yet been convincingly demonstrated, even for small systems, but we anticipate that it will be in the next couple of years, starting with small systems and then gradually scaling up to bigger ones. Now, of course, we're always going to want better qubits. And having already mentioned your neighbors at Google, let me say something about what your friends, your colleagues at Microsoft Station Q are up to. The currently most promising idea for achieving qubits which have very long coherence times and very low error for gates, at least for some gates, is topological quantum computing. One of the ideas that sprang from the imagination of Alexei Kitaev 20 years ago. And after 20 years ago, the technology is at the stage where we can hope to see convincing demonstrations of topological storage in the relatively near term. The principles are not that different from what I already described, but the important thing is that we would like to have fractionalized particles which now have a non-abelian type of identical particle statistics. And the currently promising way of doing that is to realize Majorana zero modes in semiconductor quantum wires. So one has to put together all the right physical ingredients. Semiconductor wire in a material with strong spin-orbit coupling and in proximity to superconductivity. And if we do that right, our wire will have Majorana zero modes well localized at the two ends of the wire. And what that means is that we can introduce an additional electron into the wire, and in effect, the electron dissolves and disappears, so it can no longer be locally detected in the wire. It changes the charge, but because there are large charge fluctuations due to the superconductivity, that's not easy to discern. The electron parity of the wire changes from even to odd or odd to even, but that's not something that we can detect locally. Instead, it becomes a collective property of the two Majorana zero modes at the two ends. That is, in order to tell whether I added the electron or not, requires a collective observation at the two ends of the wire. So the principle is the same as what I said before. There's globally encoded information in the wire, but it's not locally accessible either to us or to the environment. So it can be well protected against decoherence. And of course, we'd like to, in addition, do processing for such a system. So we can imagine encoding a qubit in two such wire segments, let's say with the overall fermionic parity even, and then there will be two distinguishable states, the even, and odd states, which you can think of as the basis states of a qubit. And in order to do processing, by turning off and on couplings to a third wire, we can in effect exchange two of these Majorana zero modes. And that performs a non-trivial gate on that encoded qubit. It's like rotating its Bloch sphere by pi over 2. So these are all things which, according to some optimistic projections, we can expect significant progress on in the next year. That 2018, it has been predicted, will be the year of the topological qubit when we can validate this type of topological storage and maybe even topological processing. So it's, the Microsoft Station Q folks and the experimentalists they support have really put a lot of heroic effort into this program. And of course, the vision behind it is that if we can make qubits which have really significantly lower error rates than the physical qubits that we can realize with other technologies, that might have advantage for scaling things up. And this has become a high-profile enterprise at Microsoft. Their CEO, Satya Nadella, just gave a speech last week in which he proposed a vision of the future in which artificial intelligence, mixed reality, and quantum computing will technology. So the pressure's on those guys.
He also gave an interview where he said he has no idea what is quantum computing.
Nevertheless, he has great enthusiasm.
Is there a quantum machine learning algorithm?
Yeah, well, so how can one resist putting together the two buzzwords of the day, quantum machine learning? And there are some concrete ideas about training networks using quantum algorithms where you can make an argument that there will be some kind of quantum advantage. But, you know, the state of classical machine learning is the stuff that they actually do is pretty divorced from the theory. Nobody understands how deep learning works very well. They just kind of tinker. And maybe that will change. It probably will change. And so, at least in the relatively near term, it'll be very tempting to tinker with training quantum networks and see if they have advantages over the classical machine learning algorithms. That's certainly one of the things, though I didn't mention it here, which is on the agenda for the relatively near term, just to see how well it works. Okay, so I'm trying to convey that it's sort of an opportune time, that after years of technical development, the quantum technology is really about to reach the stage where super classical tasks become possible, or where the dream of a topologically protected quantum computer starts to come to fruition. So it's an exciting time. But that's not really what our program is about, at least not primarily. I think a better way of capturing what we're trying to do is that these ideas and other ones that have arisen from our effort to understand quantum computing and its capabilities give us fresh ways of looking at a number of problems in contemporary physics, in particular at the physics of strongly coupled quantum many-body systems. So actually, let me jump to the aspect of that which I find most exciting, which is the emerging connections between quantum information and quantum gravity, which are coming to light in just the last few years. And in fact, we're finding that both quantum complexity and quantum error correction have a role to play in deepening our understanding of quantum gravity. Now, a lot of the progress that's been made over the last 20 years in understanding non-perturbative quantum gravity has been driven by the discovery of holographic duality, which is now 20 years old, what people sometimes call ADS-CFT duality. And that's really an extreme and wonderful version of emergence in a strongly coupled many-body system. The ADS refers to anti-de Sitter space, so this pertains to quantum gravity in the case when there is a negative cosmological constant, and so that space-time is negatively curved, which incidentally isn't what we really wanted to understand, because we'd like to understand quantum gravity in the real world, which seems to have a positive cosmological constant, but that's okay. This is our warm-up example, and if we can draw deep lessons from it, then we can hope to apply those lessons to quantum gravity in other contexts. But the cartoon of how it works, you've probably seen. Thinking like relativists, we have time running upward. And I can consider a system in d space-time dimensions, which I've drawn as the surface of this cylinder. And this system on the boundary is not a system with quantum gravity at all. It's a non-gravitational but strongly coupled quantum system. It's a strongly coupled conformal field theory, to be specific, with no intrinsic scale. But rather magically, it generates an emergent dimension. So it gives us a way of describing quantum gravity with a negative cosmological constant in d+1 dimensional space-time. And the amazing claim is that these are two different physical theories, and there's a precise equivalence between them. We can really think of them as two different ways to describe, two very different ways of describing the physics. In particular, when the boundary theory is very strongly coupled, that corresponds in the bulk theory to weakly coupled semi-classical general relativity plus some quantum corrections. And now, in the bulk, at least to a very good approximation, we expect to have causality, that is, no signaling outside the forward light cone. So we can ask, how is that supposed to work in terms of this dictionary that relates two different descriptions of the physics? So let's imagine that something occurs deep in the bulk. It's a bomb going off with a big bang. And to bulk observers, the information that the bomb exploded becomes available only in the forward light cone, so it doesn't reach observers further out towards the boundary until enough time has elapsed for a light signal to reach those observers. But on the other hand, there's a dictionary which precisely relates anything that happens in the bulk to something that happens on the boundary. So if we think of the explosion of the bomb as the result of applying some local operator deep inside the bulk, there should be some corresponding operator which acts on the boundary which encodes exactly the same physics. Okay? But because of the way bulk causality works, the effect of that local operator, the effect of the bomb exploding, should not be visible to any of the local observers on the boundary at the time that operator is applied. So how can that work? Well, this operator must be extremely non-local. So it does change the state of the boundary to some state which is distinguishable from the initial state, but in a way which can't be perceived locally. Well, that's just how quantum error correction works. The operator which is being applied on the boundary is the operator acting on some encoded logical system, and local observers can't see its effect because the information is encoded in such a non-local way. But then as the system evolves forward in time on the boundary, the effects of that very non-local operator should eventually become localized so they can be detected by the localized observers at just the time that this bulk light signal would reach the boundary. Okay? So this idea that there should be non-local operators applied to the boundary whose effects don't become locally visible until a later time, that's an old observation about holography going back to the 1990s. But the connection with quantum error correction, I think, was not generally appreciated until a very insightful paper a couple of years ago by O'Mary, Dong, and Harlow, all three of whom I see in the audience, I think. And what they said is, well, let's look at some particular time, slicing through the cylinder. Consider this bulk local operator, which, according to what I just said, corresponds to some extremely non-local operator acting on the boundary. But if this is quantum error correction, that means that the information is encoded in a sufficiently redundant way that it's robust, protected against errors on the boundary. So in particular, we can imagine removing portions of the boundary, erasing them in effect. And because of the redundant nature of the encoding, we should still be able to encode this bulk local operator and see the effects that it has on the part of the boundary that remains. And calling upon things that had been understood earlier about the nature of the holographic dictionary, they explained how this can work, that the bulk local operator can be reconstructed precisely on the boundary when parts of the boundary are missing. That's a type of quantum error correction, a robustness against errors. I think this is one of the freshest ideas we've had about holography in a number of years, but it certainly hasn't been fully fleshed out. And we would like to understand in greater depth how the theories which do give rise to holographic gravitational descriptions have the property that they provide very good quantum error correcting codes in which the erasure protection, the erasure correction in particular, can be done with a very small probability of error. Now beyond that, maybe we can, by looking at holography from the point of view of error correction, extract lessons that could be applied more broadly, even to asymptotically flat or de Sitter geometries. So let me talk about one way in which quantum complexity potentially comes into the story. Well, if we have a strongly coupled theory, a conformal field theory, which has a holographic dual gravitational description, we can ask, what happens if we take two such theories and we entangle them with one another? And there's an interesting answer that entanglement between these two distinct boundaries should have some counterpart in the bulk geometry. And what corresponds to the entanglement between the two distinct boundaries is that in the bulk, there's a wormhole. which connects together these two boundary regions. So it's intriguing that there's a connection between entanglement in the theory without gravity and the connectedness of space in the gravitational theory. One is tempted to draw a more general lesson that we can think of geometry as a kind of emergent property arising from entanglement in some underlying, strongly coupled and highly entangled theory. The wormhole, though, is not static. It changes with time. It gets longer. As time progresses forward. In fact, it grows so quickly that the wormhole is not traversable. So if Alice lives on one of the boundaries and Bob lives on the other, it's not possible for Alice to visit Bob by jumping into the wormhole and then emerging on the other side at the other boundary because the wormhole grows too rapidly. So having a wormhole doesn't sound like much fun if you can't go through it, but at least you can say this, that if Alice and Bob both dare to jump into their wormhole mouths and they time things right, then they can meet in the middle and have a fulfilling relationship for a while and get acquainted. But there's something I haven't told you yet, which is that the region of the space-time where the wormhole is growing is actually behind the horizon of a black hole, which means that it is the fate of Alice and Bob that they will, in the foreseeable future, get destroyed at the singularity inside the black hole. So this is kind of interesting because some feature of the geometry behind the horizon, namely the growing of the wormhole, should have some counterpart in the boundary theory. So as the wormhole gets longer and longer, what could it be that's happening on the boundary that corresponds to that? And whatever the answer is, it should be something revealing, because one thing that we haven't managed to understand very well is what the ADS-CFT correspondence is telling us about the black hole interior. How exactly is the interior, that is, the experience of an observer who falls through the horizon, encoded in terms of the boundary physics? And the suggestion, the conjecture, which was formulated, I think I saw Adam Brown in the audience, didn't I? Yeah, there he's right down there. By a group at Stanford, Brown and collaborators, was that what corresponds to the growth of the wormhole is the increasing computational complexity of the boundary theory. So what we mean by the computational complexity of the boundary theory is that suppose that starting out with some state that's simple to describe classically, like a product state, that we wanted to create this entangled state of the two boundaries using a quantum computer. But we want to do so using the algorithm which is as efficient as possible. So the fastest possible algorithm, or the time it takes to execute that fastest possible algorithm, in order to create the state, is a measure of the complexity of the state. Okay? And so the wormhole actually, in terms of sort of the natural way of measuring time, is growing linearly in time. And so what this correspondence between complexity and wormhole growth suggests is that the complexity must also be increasing linearly with time. And in a way that's maybe not a surprise if I think about on a quantum computer trying to simulate a time evolution operator. Determined by some time-independent Hamiltonian. Well, the natural way in which we would execute an algorithm which implements that time evolution operator would be to do some Trotter approximation to the dynamics and then put together many time steps. And so an algorithm like that, at best, would have a runtime which scales linearly with the evolution time that we're trying to simulate. But what's not very obvious is whether there's some shortcut, some faster way of preparing the state, so the complexity would be much less than what one would naively expect. I should say, though I won't explain, that this picture is subject to some quantitative consistency checks that it seems to pass, but at this point it's just a conjecture, and we need to understand things more deeply before we can say, before we can have high confidence in it. So let me say one more thing about this. This question of whether there's a way to shortcut the evolution. So the naive quantum algorithm would have a runtime which goes like t. Is it possible that there's a way of generating the time evolution which is much faster, like a power of a logarithm of t? And in some cases, the Hamiltonian does admit that kind of fast forwarding of the evolution. That's what Dorit Aharonov calls it. And the ability to fast forward Hamiltonian evolution is, in a sense, hidden in some of the fast quantum algorithms that we know about, including Shor's algorithm. You could ask, suppose I'm trying to measure the energy of a state with a quantum computer when I know the Hamiltonian. Well, you can do that by a procedure like this. You can consider some register that encodes the time, summed uniformly over all times, and then perform the evolution, e to the minus I ht, conditioned on the state of the time register. And let's suppose the input is an energy eigenstate of this Hamiltonian. Then the effect of that will be to encode the energy in the frequency of this state. And then we can do a Fourier transform, which is something quantum computers can do very quickly. The quantum Fourier transform is much faster than the corresponding classical fast Fourier transform. And after Fourier transforming, we can read out the energy. But let's suppose we wanted to measure the energy to very high accuracy. This procedure, just because of the limitations imposed by the Fourier transform, allow us to measure the energy, I should say the value of the energy, not the state, after we measure. And that would take a time, or the accuracy we could get would scale like 1 over the time, just because that's the resolution that we have with the Fourier transform. But suppose I wanted to measure to this accuracy in a much shorter time than a time that goes linear with t. Well, then the question is, can I fast forward the evolution, which appears inside this box? If there's a way of simulating the evolution in a time which is very short to t, like a polylog time, then I'd be able to measure the energy of the Hamiltonian, and of course I would need to know the Hamiltonian for this purpose, to an accuracy which is extremely good in a relatively short time. So this fast forwarding of evolution really is closely related to, and it's actually, as Aharonov and Adia showed, this is an if and only if statement. If we can measure energy to exponential accuracy in polynomial time, that corresponds to the ability to fast forward evolution. Okay? Now, in the case of this correspondence between complexity and wormhole growth, the wormhole continues to grow for a very long time, and so for that conjecture to be true, there should be no shortcut. The evolution of the system is highly chaotic, and it's required for the conjecture to make sense that there's no faster way of making the state, or at least no way that scales more favorably than carrying out the Hamiltonian evolution. And that's not something that we know how to show for the type of strongly coupled conformal field theory that has a holographic dual. But it's one of the goals of trying to understand more deeply these connections between computational complexity and physics. So what we can reasonably expect is that for very highly chaotic systems, like these holographic CFTs, there isn't any way to fast forward the evolution. But in other cases, let's say many-body localized phases where entanglement spreads much more slowly, it may indeed be possible to simulate the evolution at a time which scales much better than the evolution time. And so that's one of the connections between computational complexity and many-body physics, which I think is of general interest beyond this connection with quantum gravity. So what I've tried to convey is that it's an interesting time in quantum information science because after many years of technical progress, quantum technology is carrying us into a regime we weren't able to explore before experimentally, and that over years of basic research, we've developed and honed notions of quantum complexity and quantum error correction, which now are available for application to a broad variety of problems in physics. And that's really the main focus of our program on the quantum physics of information. Thanks for listening.
Crowd was quiet.
Gary.
So after Shor's algorithm, started this whole thing, have there been similar, algorithms that have shown how to sort of quantum computers can solve some classical problem much faster, or has that really been like just the one shot thing?
Well, we have a relatively small number of primitive algorithms, which are the basis for the speed-ups we know about. But the same ideas that go into Shor's algorithm actually allow us to solve problems which are of pretty broad interest. So for one example is that using similar methods, we can solve linear systems with a very large speed-up. There are caveats about that. We need to be able, so we're trying to, in effect, invert matrices by finding some solution, to x equals my, where m is some big matrix, and if we need to be able to encode the state efficiently in some state vector. So in principle, we can encode an exponentially long vector in n qubits as a quantum state. If that encoding can be done efficiently, if this matrix has some nice properties like being sufficiently sparse and not having a very large ratio of eigenvalues, then we can compute properties of y efficiently, like finding the expectation value of some other matrix in the state y. So, of course, we can solve linear systems efficiently with classical computers, but here we could solve, in principle, linear systems which have exponential size in polynomial time on a quantum computer. So that could, in principle, be applied to things like solving classical field equations, solving Maxwell's equations, and non-trivial geometries, and so on. It's one of the reasons that people are hopeful about applications of quantum computing to machine learning, is that they can speed up solving linear problems, although, like I said, deep learning today doesn't really rely very heavily on theory. But so I think, it's true that we have a relatively small number of primitive ideas on which quantum algorithms are based, but to a certain extent that's true even classically. We don't have that many tricks, but we've learned to apply them in many different ways.
By attending your talk and similar talks, I generally get the impression, very vague, that you can reach very important qualitative conclusions, such as this possibility of quantum error correction, without going to the details of ADS and without specifying even what the CFT is, as long as the space-time is a boundary, right? I mean, where did you, when you reach the argument that you could quantum correct, I think that would, at least qualitative, you don't need to use ADF. So that means that any space-time with a boundary, I mean, anything with a space-time boundary would work.
Well, I'm not sure about that. I think so part of what Almairi, Dong, and Harlow did is they pointed out that things that were already known about the holographic dictionary, about the procedure for encoding a bulk local operator on the boundary, have the property that we can do the encoding on a portion of the boundary when part of the boundary is erased. So I think the qualitative ideas I described are plausible on general grounds that there is to be a holographic correspondence, but it was very nice to see it fit together with things that were already understood about the dictionary.
I wanted to understand better what you were saying at the very end. Were you saying there are condensed matter systems where you can fast forward, and you wanted to contrast that with ADS-UTT?
There are some, but and we can also say this. We can also say that there exist local Hamiltonians based on complexity theory reasoning, such that evolution for a super polynomial amount of time cannot be fast forwarding to the point where we can simulate it in a polynomial amount of time. Because if we were able to do the fast forwarding for any local Hamiltonian, then we'd be able to solve hard problems, which the complexity theorists say are it's widely implausible we'd be able to solve. But that doesn't tell us about whether or not a Hamiltonian can be fast forwarded in any specific case. But in fact, there are examples you can write down of Hamiltonians for which the fast forwarding is possible. But if I give you a Hamiltonian for you to answer the question, can this be fast forwarded or not, that's not an easy thing to do. We'd like to get better at that. And again, the complexity theorists can help us if we have a way of saying, well, for this particular Hamiltonian, we have a way of encoding algorithms that solve hard problems, which we could do efficiently if we could fast forward things. Then we'd be able to reach a non-trivial conclusion. We'd like to understand that better.
Yeah, I wanted to understand, that's great to hear more, but I wanted to understand also the contrast you're making with holography, just because we know we can model various condensed matter-ish systems using holography, and it's a much broader thing than just the CFT case. So it's.
I see. Well, maybe, yeah. It's interesting to ask what kinds of deformations of the CFT would allow fast forwarding, even if right. In the critical system we can't do it.
Right.
Yeah. So I just want to make a comment a little bit about your response to Gary. So I think that we as physicists. Usually we complain that there's too much hype, but I would say actually we've undersold the interest of quantum computing because we've allowed ourselves to be misled by the computer scientists into thinking that we have to justify quantum computing by saying that it's good at solving classical decision problems. So I think, why? We're physicists. We don't care. I don't care about factoring. I don't, or a semi-definite program or something. I mean, the thing a quantum computer is good for is solving quantum computational problems like quantum simulation. And there it's immediately obvious that there's tons of interesting applications that are going to be very useful for us, when we have 50 or 100 qubits. So we don't need to talk about waiting for 10,000 qubits to solve some classical problem.
Yeah, it's always good to have a plant in the audience.
In fact, that might first have answered the question, but is there, so far the mindset was sort of using quantum computing as a tool to answer the same types of questions we had been asking and trying to do by classical computing. Is it sort of better to switch, or is it useful to switch the mindset to sort of ask different types of questions? And if so, what are the types of questions that we should be asking that quantum computing would be particularly useful for?
Well, I think Daniel just gave us an example of that, right? The nice thing about factoring is it's a problem that's, as we say in NP, it's easy to confirm, to check the answer once the computation has produced the answer. And so it's nice to be able to validate that the computation was done correctly. But there are a lot of problems that we're interested in that just aren't in NP. They can't be easily checked. And quantum simulation is sort of a prototypical example, which raises the issue of how will you validate a quantum computer which solves a quantum simulation problem. And there's a lot of people are thinking about that question too. But I mean, part of the answer is you do the computation in different ways with different hardware and different algorithms, and you can check the results against one another.
Well, thank you very much, John.